Okay, so today I'm just going to go over another example of designing in Vivado. By this point, because of the lab that we had on Monday, you guys are probably feeling pretty confident and comfortable, but I just want to make sure that you're all the way there. If you want to move up somewhere closer so you can see better, you're welcome to, since there's nobody here. I'll make the text bigger as well once I open the design file. So by now, we know how to make new projects, right? So new, next, give it a name. I'm going to call this one ECE 2700. We're going to build an equity detector. The name is really long simply because I have to differentiate between, every semester and everything else. If you just wanted to call it equity detector, that would make sense. And when I say equity detector is we just want to build an n bit, so variable bit more or less, equity detector. We want to be to say, hey, are these two numbers equal? And there's kind of an easy way to do this, and I'm going to intentionally make it more difficult just so that we can kind of illustrate some of the ideas. So again, we stick to RTL projects, and Jason, if you have a laptop and you want to get it out and follow along, it's probably a good idea. Okay, so down here, make sure when you create the file, it says VHDL. This has been a problem for many students. So you're going to notice the main error, the visual clue that you forgot this, is that the color scheme inside of the text is wrong compared to the examples that I go through. And then you'll get weird errors that don't make a lot of sense as well. Here, when we get to the default part, as I said before, I use the basis board. Realistically, for this class, if you just picked any one of these parts, you're probably okay. But I'll stick with the basis. And then it takes a little while to get started. What I want is for this portion of the creating a project, setting up your files to be kind of just instinctive. So we're going to add source by clicking this plus button inside the sources or the add sources. We always are going to start with design sources. And then we have to create files. Now, just like the other design, like the full adder design, I want to build an equity detector 1 bit at a time. So I'm going to build a 1-bit equity detector. Okay, so I'll call it equity 1 bit. Okay, so once I've done that, equity 1 bit shows up underneath here on the design sources. At this point, I'm going to pull up my settings for the file, and this is just for you guys' benefit. I can go to text editor and fonts and colors. Okay, I'm already set to 37. So if you ever wanted to change your font size in the text editor, this is where you could do it. And you can even change some of the coloration here. So like if you didn't like working black on white text, you can change the background and foreground. And then I can open this up. Move that. And make it big. Okay, so as usual, I'm going to go ahead and, well, I'm probably going to have to shrink this text a little bit. It's kind of big. But I'm going to uncomment the numeric standard library. The numeric standard, in case you've forgotten, is a library that adds signed and unsigned number types. We don't do a lot with this, but when we do that, you can also use the plus, minus, subtract, divide operations on unsigned numbers. So I can't do that on standard logic, but I can, if I have the numeric standard library, take a vector, so a standard logic vector, and convert that to a signed or unsigned number, and then do those math operations on it. This Unisim library that we have not uncommented yet adds a lot of what we would call like default parts that make it easier to work with Xilinx FPGAs specifically. So Xilinx is one of the big two FPGA makers. There's Xilinx and Altera. Altera is now owned by Intel. So for Xilinx, if they want you to use certain parts, we will do that in 3610. We won't do that in this class, so we can just delete that. And as I said, I'm going to reduce that font size just a little bit so that we can actually fit some code on here. Okay, there we go. That's more reasonable. Can you still see? Yeah. Okay. All right. So there's a couple different ways to design this, right? A lot of times for students, especially when you're beginning, you would want to go ahead and draw what does the circuit look like, right? The visualization of that block diagram can help you identify the ports that you want to use and create. The other way of doing it, which I'm going to do here, is just kind of start writing your code and identify what you need as you go along. And you go, oh, I need a port here or a signal there. So this kind of discovery programming works well too in Verilog, especially in these smaller modules. The larger and more complicated you get, the less well this works. So if my goal is to detect if 2 bits are equal, there is a really easy way of doing this, right? So let's start with, well, I need 2 bits, A and B. They're in, and we're going to call them standard logics. Okay. So what is the simplest expression someone can come up with where F, which we'll call my output, let's go ahead and make that, right? So I go, oh, I need an output. So I'm going to call it F of the mode out and the type of standard logic, right? So if I do that, what is the simplest assignment that I can do to F that says F is equal to 1 if bits A and B are equal? Exactly, yeah. You can do an XOR, an inverted, or XNOR, right? Because in XOR, it's true if they're different. XNOR is true if they're the same. So all I have to do is A, XNOR, B. Perfect answer, right? And F is done. Let's see what it does not like. F is not declared. And that's because of this error here. And it wants a semicolon instead of a comma. So that error popped up just because I had the syntax and it was like F isn't declared because I had an error up here. That can be one of those kind of cascading errors that you run into. Now, much like the adder, we want to be able to chain multiples of these together. Now, one way of doing that would be to just output a bunch of Fs and take them into an AND gate, right? Because if I had, this detects 1 bit, and if this F is output for true of N bits, right, then you would just AND them, and if they're all true, then you're good. But let's say we're trying to design a power optimal design. So the outputs are only ever going to change or be evaluated if the previous bit is true, right? So if I do it all in parallel, it's faster, but will consume more power. So let's do it this way so that we're going to cascade them, much like the ripple adder that we designed in lab. And now we need another output to do that, right? We need something like an enable. So I'm going to go ahead and say F comma EN is also an output. That also means if I want them to be able to take an input, then I need to take an enable in. So I'm going to change this en output to en underscore o that says, yes, we're good. I'm also going to add en underscore I for input. So this is something you'll see very commonly in notation for VHDL, where you'll see underscore I underscore O for inputs and outputs, so that you know what that signal is supposed to be doing. The other one that you'll see is if, say, you needed a signal. So if I came down here, signal C is type standard logic, right? So we did something like this to create the connecting C in our ripple carry adder. A lot of times what you'll see is underscore S that says this is a signal and only a signal. And this is beneficial because when you get to your debugging time, right, when you're looking at those waveforms and you see an underscore S, underscore I, underscore O, etc., you go, oh, I know what this is supposed to be doing. We don't need any internal signals yet, so I'm just going to go ahead and, well, let's comment it out just in case something comes up. So dash dash is a comment. Okay. Now, what is the case, and this is going to be kind of funny once you realize, because this is what I mean by I've made this more complicated than I needed to. What is the case for enable in? Where do I use enable in? Yeah, and we can do that really easily with AND gates. And ENI. So the only time that F will ever go to true, will ever be asserted, is if I have A XOR B and it's enabled. Now here's the super trivial one. Well, enable out is true if, well, it turns out if F is true, right? Because it's saying if this bit is equal, then we'll send out the enable. You could do something like this and say enable out is equal to F. It's going to throw an error because it says I can't read from out objects. What that means is I can't put an out on the right side of an equation. Now, the bad way of fixing this is I could change F to the type in out, which means it can be an input or an output. And what this does is it goes back to the tri-state logic, which we talked only briefly about, which is where you have an extra situation. Instead of pulling up to 1 or down to 0, it just sets to what we say high Z. But that's not the good way of doing it because F isn't really an in-out. I've just put it on a different step. So a different way of doing that is saying something like the signal, let's see if this works. Sure, I'll just call it CS. Why not? Not really an issue. And I could probably say CS is equal to F. Oh, wait, nope, that's not going to work either, right? Because I've got F on the other side. So I'll show you the most right way to do this probably here is just copy and paste the F or get rid of it, right? And just not use the enable. But as I said, I want to make this arbitrarily more complicated. So normally you might have more complex enable situations. This one is just a repeat, but it now has that extra port that I want to use. Okay, this is now my 1-bit equity detector with an enable in and enable out. So let's go ahead and create my larger, I don't want to say top yet because I'm not there. So we're going to go ahead and build a 2-bit equity detector. Okay, there we go. So there is, some of you have noticed, there's been a recent update where the settings aren't carrying over very well. So I have to go open up settings and just change it and change it back and then hit OK, and it will update this. I don't know why. Hopefully they update again soon to fix that bug. Okay, so here's where we come in and we say, well, the 2-bit works off of the equity 1-bit. And we always like to start by just copying and pasting the entity declaration. Now, hopefully some of you have discovered why this is important, because I've seen your errors, right? Where you've gone ahead and not copied it over and you type them out and you've missed ports. And that's a problem, right? Is you're going to get pretty weird errors that are difficult to debug when you do that if you're just missing ports. So that's why I strongly encourage the copy and paste method. Once we have this component declaration, right? This is declaring that this component exists. I need to create instantiations of that component. So let's call it EQ0. It is going to be made out of this equity 1-bit, and it's going to have a port map that needs all of those ports. And the way I'm going to do this is I'm going to create, and I strongly recommend you all do this too, because I've seen a lot of errors here. Just start by creating all of the ports this way. Because if you start with the ports existing, you're not going to forget that they're supposed to be there later. Whereas if you don't create all the ports at first, it can get pretty easy to accidentally skip over one and then not realize it even when you go back and look at your code. And I've already seen this with a couple of students, so it is a real issue. Okay, so I'm going to have these errors floating around because I've done bad code, right? I've left a lot of blank spots. Now, it is always true that the port is on the left and the signal is on the right. This is flipped from the assignment statements, right? So for F, I have this kind of arrow saying I'm putting this equation into F. Well, here it's kind of going the other way and saying I'm plugging this port into this signal, which is kind of confusing sometimes. But that's why I recommend starting with the ports, because if you just remember, okay, all of my ports are on the left. Now I can go and attach signals on the right. Well, the nice thing is at this stage, I can just copy this whole EQ0 and name it EQ1, and I have now a 2-bit equity detector ready to be filled in. I just have to tell it what it's connected to. Okay. So what are they connected to? This is, again, kind of that discovery coding, right? Which is going to get a little trickier now that we've gotten more complicated, but it's not too bad. And we're going to say, well, we need 2 2-bit vectors, right? Just like the 2-bit full adder. Nothing different. But, and I strongly encourage you to do it this way, don't use A and B. Use a different port name. And you could be like N0 and N1 is a perfectly fine thing to do. I just want you to make it different. Eventually, if you're doing a big complicated design, it gets difficult to make all of your port names different. But for now, especially as you're learning, it's beneficial. Remember, mode is going to be in, and the type is going to be standard logic vector. Now, we need the 1 down to 0, right? Because we're 0 index, that is 2 bits. Our output is going to be, let's just call it O. I'm trying to think if that's going to be problematic later. Not sure. Let's leave it as O. Actually, we're going to call it E for equals. standard logic vector. It is also, well, sorry, no, this is just going to be standard logic, right? And let's see what my error is. Oh, I added an unnecessary colon. There we go. So something that I can already see is missing here is if I wanted this 2-bit to be able to cascade into 4 bits, right? They also need enable input and enable output. Okay, now I could build this into, just like you could with your full adder, into 4 bits. Right now it's 2 bits, but I could string multiples of these together into 4 bits. Okay, now where do these detect? The right side is signals. When I declare ports, it creates for me both a port and a signal to use. So I don't need to go and create unnecessary signals here. So I'm going to know I need something with N0, something with N1, right? Because those are what I'm comparing. The enable input is probably going to come from this enable input. And then the F output, okay, this F needs to go somewhere and do something, right? Well, it actually turns out, because of the way I've designed this one, I can ignore this F because I've duplicated an F in this enable 0, right? So the 2 ways that I could build the overall equity detector is the one where I take this F and attach it to an AND gate, and this F and attach it to the AND gate. And I can say if all of these are true, then they're equal. In this case, I don't need it. So when you do this type of explicit port mapping, I can just delete a port. It's gone. It's not a problem. And then I can go ahead and say my enable O, and I go, well, I need to somehow attach this enable output to the enable input of the next one to say, hey, you should go compare, right? This is where the internal signals come into play. So now I'll go signal, and I need to come up with like a good name for it that describes what it does, and I'm going to just call this cascade enable. Yeah, there we go. Now, I'm putting here as an output, and the enable input is an in. So what that does is this cascade enable is connecting the output of the first one to the enable input of the second one. We're going to do this kind of internal connections a lot coming up. Okay. Now, I left it this way on purpose to show you an error that you're going to see fairly often. Is if I mouse over this, I know it's small, so I'll just read it. It says error, type error near N0, current type standard logic vector, expected type standard logic. So sometimes this is really useful and sometimes it's really confusing. In this case, it's really useful because it's saying it is a standard logic vector, but I'm expecting a standard logic, meaning you've given me lots of bits and I really only wanted 1. And what it's doing is it's prioritizing the port. That port only takes 1 bit, whereas N0 has 2. So we're going to give that vector a location. So we're just going to pull out 1 bit of that vector. Now, I have another error. Let's figure out why. Type error near NI, current type standard logic vector, expected standard logic. Here was my issue. So when I created enable I the signal, and here's why creating multiple ports with the same name is dangerous, is because it says near NI, enable in. Which NI? Is it, because you know I can double click on it and it highlights all instances of NI, enable I. And so it could be the one that's associated with the component, or it could be the one that's associated with the entity. Well, in this case, it turns out it's the one associated with the entity. Because I've created this enable input as a vector, but I don't want a vector enable, right? I just want a bit. So I'm going to have to create a new line. Using, and its type is still in, but its mode is still in. Its type is standard logic rather than standard logic vector. And now my errors are gone. Notice I am missing a port, right? I deleted that F, but there's no error. So you can do this, it's fine, it's allowed, but you need to understand and do it on purpose rather than accident, because it doesn't throw you an error or a warning. It would just disappear and you would be completely lost when you do that if you accidentally did that. And I've seen it happen on the adders already. Okay, now we have this kind of template and we know what we're doing. We're going to say n 0 at 1 and the vector n1 at 1, right? So we're taking the second bit of that those n vectors. And then I've already connected the cascade enable. The F, again, I don't really need it, but I'm going to go ahead and use it as E. That is, E is my equal. They are equal. So the port F on the second one is E, and the enable out of the second one is going to the enable out of the entity. So we're just passing an enable through potentially. Now I have two equity 1-bit detectors. Hopefully I can string them together and build that into a test bench that works, right? This is the same thing as what we did with the full adder. Do I have any questions on the equity detector so far before I switch over to building the, my mind just blanked, the test bench? No questions? Okay. So test benches. You guys have done pretty well with these, actually. I'm really happy with that. We're going to hit the add sources again, but this time we're going to create a simulation source. We're going to hit the create file button, and we're going to give it a name. Again, I strongly recommend calling this essentially the same thing as what you're testing with underscore TB at the end. So I'm going to call it equity 2-bit underscore TB for test bench. This helps both of us really, because if you get in that habit, you're going to see it in industry. I think all 3 companies I've worked with have that standard requirement, like you have to do it that way or they get upset with you. And I do it that way. So when I come and help and I look at your code, I can understand really quickly what your files are trying to achieve. Okay, then we can hit finish here. In this design environment, right, I want you guys to be kind of familiar with it. I make this whole code big. To get back to sources, there's just this little tab on the left side that says sources. I can click on it, and then underneath simulation sources, there we go. Underneath simulation sources, I know these texts are kind of small. I'm going to see that underscore TB, which I can then open up. Again, because there's this weird bug happening with Vivado, I have to go back into my settings, change its size, and hopefully not crash it. There we go. So remember to save often. You can save just with Control S, or you can find this little floppy disk button that sometimes they have and sometimes they don't. Here we go. The floppy disk button, which I know most of you are young enough, you've never seen one, but it's there. Okay. I'm going to do all the same things I did to prepare the file. Now, a test bench, though, never has ports. I've said that a lot. You can expect it to show up on an exam sometime. We just don't do it for the scope of this class. I've never encountered it. I'm not going to say that there's no situation that you would want a port, right? There's maybe an exception to the rule that I've never encountered, but I just haven't run into it yet. Okay, so also on the test bench, because I have no ports, I need to create all of my test signals. Well, before I create my signals, let's go ahead and create the component, because that's what really tells me what signals I need. And again, copy and paste the entity of the thing that you want to test, because that will prevent you from missing any of those ports. So I jumped back to equity 2-bit, copied its entity declaration, go back to the test bench for it, and just paste it, changing the word entity to component, and then changing it to end component. Now again, the declaration is just saying this exists, and I've created an error somewhere. Oh no, it went away. Took a little while to update and realize that it was okay. All right. And now I can create the instantiation. Now I'm not chaining two of these together yet, but I actually could. If I really wanted to in this test bench, I could chain multiple of these components together and see how they react. All right. EQ2, I'm going to call this one EQ2B, or equity detector 2-bit, and then I'm going to underscore UUT, so that I know that this is my test unit. Unit under test. Its type is equity 2-bit, which I like to copy and paste the name, because I in my night lab, which was just yesterday, I spent 20 minutes helping someone debug their code. They were trying to, I'll just type it up here because it's kind of funny to see, and it took me forever to figure it out. They were doing the full adder, so they typed FA0. Does anyone see the issue with that full adder declaration just from what I've typed? There's 3 Ds. Right? Do you see how hard that is to see and identify? It took me 20 minutes to find that for someone, because I was mousing over and it was saying this error that was like, full adder does not exist. And I was like, I can see it right there. I've declared it. And I spent 20 minutes trying to debug it just because of that little typo. So that's why I like the copy and paste so much, is because it's way less chance that you're going to get a mismatch on the naming. Okay. Port map. And then I'm just going to go through. I'm not going to say them all out loud. I'm going to just create all of the ports to start. Okay, so now I've got all of the ports and their little commas. Some of the things that I can do to simplify a little bit is I know that I always want my first one enabled if I'm running this test, so I'm just going to hard code that to 1. I know that I'm not cascading anything, so this en out isn't really going to do anything for me, so I can delete it. And now I need to go back and go, oh wait, I need signals for these. Signal, well, let's see, what did I call my last one so I don't do any overlap? So last time I was calling it cascade enable, so I don't want to use anything like that. Signal n0 underscore tb is a great way to name these variables so that I know that the signal I'm dealing with is the test bench signal. And I can just do that on the same line, just like I can in the port for N1, because they're the same type, meaning that they're both standard logic vectors. If I have a signal of a different type, like, well, if let's see, I don't really need, the ENI, I don't really need to create a signal for that because I'm just going to hard code it to 1. But if I were, I would create another signal ENI underscore TB of type standard logic. So you don't want to do or can't do 2 rows, sorry, different variable types on the same row. And I have an error here, and I need to figure out what I did wrong. Oh, I missed the colon. So you'll see that these errors are sometimes a little bit difficult to spot and sometimes really obnoxious in this. So if I mouse over it, it just says syntax error near standard logic vector. So as usual, to me, that means look right before wherever the error is. That's usually your culprit. So right before the standard logic, I went, oh, I need that colon. So the error tells you where the next thing is that has an issue. And it usually means that the error is right before it. Not always, but it's the best place to start searching. Now I can do things like tie in N0 test bench the signal into the port and N1 the signal into its port. And then, oh, look, I need an E for equity. So I'm going to create a signal, and I'm going to actually call this one equity. I am going to keep the underscore TB so that I know where it's associated with, and it too is going to be standard logic. Okay. Once I've done that, I can start creating what we call the stimulus. We want to stimulate the circuit. We want to see what happens when we do something to it. So we do that inside of a process. We're going to get a lot more into processes next week, actually, I believe. Okay, so we need to start initial values with things. So there's a couple ways that we can do that. The easy way, and the way I've shown you before, is I just say this N0 TB is equal to 0, 0. And I use quotes because it's a vector. I use apostrophes if it's just a bit, right? And I do the same thing for the N1 underscore TB and assign it to 0, 0. Now, another way that I could do this is up here where I have N0 and N1 on that line. I can do this where I do colon equals 0, 0. So on that line 38 here, this colon equals 0, 0 is setting a default value. But this is a little bit of a trap. If I were to do that in this equity 2-bit, it would simulate correctly, but would not run correctly if I were to turn it into a real circuit. So it would not what we call synthesize correctly. It doesn't create default values very well Now, the bigger risk of this is sometimes it works, because what's really happening is you're saying I'd like it to start at 0, 0, and if it can do that, it will. But if it's more optimal to not, or if the universe hits it with what we call a cosmic ray, which is just a high energy burst of radiation from space, it can just flip that bit because it's not hard coded. It's just kind of like a suggestion, essentially. And that's not exactly what's going on. There's like way more complicated stuff going on behind how it assigns it. And that's kind of more 3610 junior level topic. Just understand the main point is if you do a default assignment in code and you try and synthesize it, it's likely to fail and confuse you later. So if your code relies on starting at a specific value, you need to use what's called a reset, and you need a memory component, which we don't know yet. We will learn that soon. So for now, be very careful to not use default values inside of design sources, but you're fully welcome to use them inside of simulation sources. Okay. Now, we have this wait for statement that we like to use, and we give it a time. We can either create a constant like I did back in like 2-3 weeks ago, or we can just write 10 nanoseconds and be just fine. I like 10 nanoseconds. It's a reasonable length of time in the circuits for our purposes. And then we want to test, if I say exhaustively, all possible combinations of N0 and N1. That means I'm going to need 16 lines, right? 2 to the 4 lines of a truth table. So the easiest way to make this test bench, until I teach you for loops, because you could write a for loop on this one. I haven't taught it yet. We'll get there. If you're not using a for loop, the easiest way is to kind of plan it out in advance. So right now I'm at let's see, I can doodle. Annotate. So if I have a truth table and I have an N0, 0, I'm going to change this up a little second. Sorry. I just want to make sure that this video translates well enough. Oh, and I'm going to flip these ones and zeros. Okay. I have a truth table that looks something like that, right? Well, you know that we're going to have 0, 0, 0, 0 in the first row, right? Well, N0, even that 0th bit, is never going to change until you've gone through all possible combinations of N1. So it's going to be 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, right? And so on and so forth. What we want to do is just recreate that in the process and just step through all possible lines of that truth table. So how do we do that? Well, the easy way is I now have my default value. I'm at 0, 0, 0, and I only need to change N1. And it's going to change to 0, 1. And then we're going to wait. Now, the reason we wait is if we don't, these all happen instantaneously and we won't see anything on our test bench, and that's a bit of a problem. Now I can just do a little bit of copying and pasting here to save myself some time because I'm not the world's fastest typer. And I have 0, 1, change this one to 1, 0, and change the third one to 1, 1. Now I've done all possible combinations of N1 for N0 is 0, 0. Well, if I just copy this whole block and paste it, and I change N0 to be 0, 1, now I already have all possible combinations for N1 when N0 is 0, 1. Rinse and repeat. For N0 is 1, 0, and for N0 is 1, 1. So I've separated them out like this so you can easily visualize those blocks of code, which are really the blocks of 4 lines from the truth table. Right? Now, simulation. Just run simulation. You've all done this now. You've all got waveforms.
Wave or wave?
Waveforms. This is a little bit suspicious. Normally it doesn't take this long to run, so I'm a little bit worried that I've done something wrong somewhere and it's got stuck in a loop. So I'm gonna hit cancel for a second. One thing that you can do that is helpful is at the very end, you can add just the word wait instead of wait for anything. And what this will do is when the simulation hits that point, when the simulation hits that point, it's just gonna stop. If you don't have that wait, what's going to happen is it's gonna start circling around and it's gonna run over and over and over again. And it can be hard to tell what the full extent of your simulation is. My laptop went into power save mode. I think that was the issue for why it was taking so long. Yeah. Okay. So I'm going to minimize these other windows for a second, just so we can go ahead and look. Remember, there's this little sign that says zoom fit. That's the 4 arrows pointing outwards. I like to start there. Now you can see here how kind of nice it is that when I use that wait, I can clearly and obviously see when things stop changing, right? So this yellow line, I'm no longer providing any new stimulus, so it's just kind of stopped. Now this orange line, the U, is saying that there's something undefined, meaning I haven't assigned it a value. So this could be a problem. I know it's not, but I left it here on purpose. So the reason is because I created the signal ENITB with no default value and then never assigned it. The reason it's not a problem is because I didn't tie the enable signal in the test bench to the enable signal of the UUT. I just set the UUT to 1, right? So it's not an issue that I didn't set that, but I wanted to show you all what that looks like. Okay, so now we can zoom in a little bit. And this bottom line of the equity TB is if it's a 1, they're equal. So here we have 0, 0, they're equal. At this yellow bar's time step, they're not equal because it's 0 and 1. Now, you can right click on this. So I'm going to right click on N1 TB, go down to radix and change that to binary. So now let me zoom in a little bit. You'll see that it says now instead of decimal of 1, 2, 3, it's binary of 0, 0, 0, 1, 1, 0. So depending what you're looking for, changing the radix is useful. But I'm going to go back to the unsigned decimal. And I can go through and see that there are 4 cases where they're equal, which makes sense, right? 0, 0, 1, 1, 0, 1, sorry, 0, 0, 0, 1, 1, 0, and 1, 1 are the cases where there are equal 2-bit numbers. Great, it works. Now what I want to show you is kind of a lead up to some of the design problems that you're going to run into in the real world. Actually, first, let me show you something that's kind of useful for turning in labs and assignments. If you're on Windows, which it looks like almost everyone that has it out is, I'll start with this disclaimer. You can make this work on Mac, but it's a nightmare. It's very difficult to make it work on Apple. It's difficult to make it work on Linux, but it's crazy difficult to make it work on Mac. So if you've done the easy way and you're running it on Windows, you can push the Windows key, Shift S, which is going to bring up this little crosshair cursor, and you can just draw a box around part of your screen. Now, wherever I do that, box is now copied, and I have that image. That makes it really easy to submit homeworks of waveform pictures. I just wanted to show you guys that. Okay, so let's create a problem. Now, this is a ripple effect, right? So I'm going to go ahead and jump into my test bench and do what I said I could. And I can build a 4-bit equity detector just inside my test bench using a 2-bit equity detectors. And I'm going to change UUT2. I'm going to need to then attach. So the enable 1 is always in true, but I need to go back and add the port ENO to the first one. And it's going to need a signal ENI TB that I've already created, which is going to be used as the input enable for the second one. And now this N0TB has a bit of an issue because I really want it to be 4 bits. So I'm going to upgrade this to 3 down to 0 and default it to 4 zeros. So if I don't change that, if I try and initialize a 4-bit vector into 2 bits, notice how it's not throwing me an error. Sometimes it will, sometimes it won't. I don't know why. But once you try and run that simulation, it'll throw an error. Okay. And now I have the other issue, and this is really kind of an interesting problem that it's not throwing an error because N0TB is 3 bits or 4 bits and N0 is 2. I'm sure once I tried to run the simulation, it would have an issue. Okay, now I have 2 2-bit equity detectors tied together. I up the equity output from the first one because I don't care really. And we can go ahead and make one more change to this circuit. So what I want to do is show you another code that doesn't work in real life, but it works in simulation. So circuits have a delay. I've been alluding to this for a while, and we're going to learn really about what that means soon, but I wanted to show you why it matters, why we're concerned. So let's say that the F changes after 5 nanoseconds. So here's a new keyword, after 5 nanoseconds. Now, the clue that you know that this isn't going to work in synthesis in a real circuit is real circuits don't know what time is. They only know that clocks are a thing. We haven't even started talking about clocks yet. So after a delay of 5 nanoseconds, so you would normally come up with kind of an estimate of how long your circuits would have a delay and then put this into the circuit. So now when I go back to the simulation, I don't have to close the simulation, run it again. I can just push this little circle loop button here to relaunch the simulation. And easy, it will pull in the new code that you've written and update it. Uh-oh. Let's see. I've made an error somewhere. Expression has 2 elements expected 4 in equity detector. So here I'm in the TCL console to go read this error. And the text is really small for you guys. So what I'm looking at is it says, I went and find the first error. So what happens is it kind of cascades through a series of errors. I go and start with the first one. And the first one says my expression has 2 elements and expected 4. And then at the very end here, it's telling me it's in equity 2-bit TB on line 59. So on line 59, here, I didn't go back and change those, right? So I'm trying to assign a 2 bits to 4 bits. So I'm just have to go add a whole bunch of zeros. Okay, let's try this again and hopefully it works. This is kind of why I like doing these sessions sometimes is I'll run into weird little errors that you guys are also going to see, and I can help teach the debug here. Okay. Let's zoom in and have a look. So 0, 0 is kind of the uninteresting case, but notice that here at 1, 1, it's true starting at the yellow line. But the equity detection doesn't happen until 5 nanoseconds later. There's a bit of a delay at. So this is okay. Not much of a problem as long as we understand that where that delay is coming from and we design a circuit accordingly. But if there was a worse situation where the enable takes a long time, so I've just changed that after 5 nanoseconds to the enable signal. And this is part of the reason that I wanted to add the enable signal, even though you could just use the equity detection out, is I want to show you these what we call delay paths. Okay, so here, 1, 1 at this yellow line, equity should be true. Instead, it becomes true all the way over here when 1 and 2, because they're not equal as far as the equity detector knows. The numbers are unequal, but they're still trying to compare this thing way down the line. So what you can visualize this using is if I open up the scope tab and then objects, I can actually go inside each of these and start throwing in bit by bit the individual enable signals. So here I'm in EQ1, enable I. And I'm just going to go through each of those components and pull out their enable inputs. So that now I have 4 enable inputs, and I can rerun it. And we can actually see the ripple. So here goes equal, passes on to the next one, passes on to the next one. And actually, I'll zoom in a little bit more to make it even more obvious. Okay, so right at this yellow line, we become equal. 5 nanoseconds later, it goes, oh, look, we're equal. 5 nanoseconds later, it is able to pass that message to the next one. And 5 nanoseconds after that, it passes to the next one, and it finally ripples to that final equity detection. We can see that slow progression through and how that can cause a problem, right? And in fact, your adder can do the same kind of thing, and it starts looking like a random number generator almost instead of addition when you're offset by weird amounts. So these delays are real problems that we can simulate and try and identify, but generally we just try and avoid them, which is some of what we'll talk about in upcoming classes. So that's what I wanted to show you is kind of this design process, walk it through again, make sure it's hammered home, and show you some of these kind of concepts of how I make sure it and run into some issues, right? If anyone has any questions, we've got some time left in class. I would be happy to answer them. Yeah.
What would an after signal be useful in design?
Say that again.
What would an after signal be useful in design?
Oh, so like in this case, it would be useful. So if I could go in and try and estimate how slow my gates are, then I would put those after signals in so that when I simulated it, it behaved how I expect my real circuit would behave like my simulation. Because if I don't use those after signals, it just happens, right?
But in real life, there is actually a delay.
But in real life, there is a real true delay, and it doesn't simulate that unless I tell it to.
So we're compensating for the real life.
Yeah. Yeah. Other questions? Hopefully VHDL is almost getting boring, right? Not confusing. It's just old hat. Starting the first thing next week, we'll jump into circuits with memory. How do we hold on to things? How do we remember what happened before? And we'll start building from there. This is where it starts getting exciting, and we can start building some really fun and interesting things. All right. I guess you guys can bounce a couple minutes early.